Again, just to remind you, a colligative property is just a property of a solution. It's a property that affects the solvent, but not the solute, all right? And the first one we're going to look at is what happens when a solute is placed in a solvent and it lowers the vapor pressure of the solvent. Now, volatile means that you have a liquid with an appreciable vapor pressure over it. And most of the time, the solvents are volatile. They'll have a vapor pressure over it. Once in a while, if you have a really heavy molar mass substance, you won't, but most of the time you do, okay? So I'm going to show you a video here in a second with two little Erlenmeyer flasks. They're both capped, but the left-hand side has only purple solvent molecules. And you can see that there are purple solvent molecules in the liquid, and there's also purple solvent molecules above the liquid. So the ones above the liquid would be the vapor pressure, and the ones dissolved in the liquid there, those would be the solvent molecules. Then we're going to look at the same set of conditions on the right-hand side, but those red molecules are solute particles. We're going to assume that the solute is non-volatile. It doesn't have a gas pressure of itself, but it will affect the gas pressure of the solvent over the solution while we're set. Now, we're also going to see how this is affected once the liquid vapor equilibrium hits. That just means that you've given them enough time for the vapor pressure to establish it. Pretty cool. So let's see how this is going to work with our examples here.
The vapor pressure of a liquid depends on the ability of the liquid's molecules to break intermolecular forces and escape into the vapor phase. A molecule can escape only when it has enough energy and is at the surface of the liquid. When a non-volatile solute is added to a liquid, some of its molecules occupy surface sites in the liquid, displacing volatile solvent molecules. Because fewer solvent molecules get to the surface, fewer can escape, and the vapor pressure of the solution decreases.
So again, on the left-hand side, you're seeing a normal solvent, and most solvents are volatile, which means they have a vapor pressure over them. And so if you have a closed system, then eventually this equilibrium happens between the liquid and the gas phase. You're going to have some vapor pressure over the solvent, no problem. And that's how most solvents are. On the right-hand side, though, we're adding a non-volatile solute. So non-volatile means that the solute doesn't have a very big vapor pressure. So it doesn't have red molecules floating above the solution, basically, which is the case with a lot of solutes. But anyway, the red solute molecules block the liquid solvent molecules from going into the gas phase. The solute red molecules, they don't care if the purple molecules in the gas phase go to the liquid phase. That's not a problem. But they do prevent the liquid molecules from going into the gas phase. So what happens, solutes tend to block the solvent going from liquid to the gas phase. So you end up with less liquid molecules in the gas phase over the solution, and what that means is your vapor pressure is lowered. So if you were to measure the pressure on the left-hand side Erlenmeyer there without the solute, it would be a higher number than the vapor pressure of the solvent on the right-hand side where you have a solution. So in a solution, the vapor pressure of the solvent is lower than it is if you have the vapor pressure of a pure solvent. I like to think about the solutes as being like blockers at a nightclub, or bouncers, all right? Like they're like, you know, they look at people and they say, oh no, the club is full, you can't come in. But once in a while they'll let people in. They're popular, which I never understand because I'm not popular. But anyway, that's a personal problem. Anyway, the blockers, the bouncers, prevent a lot of people from going into the club. Now, people can go out of the club anytime they want. That would be like gas going to liquid. But they don't let a lot of people go into the club unless you're special. All right. That's a really dumb analogy, but it does kind of reflect here how the solvent molecules have an issue, have a problem going from liquid to gas when the solute's present. They are literally bouncing them back into the solvent, and it takes extra energy to let the liquid molecules, the solvent liquid molecules, get into the gas phase. So at the end of the day, the vapor pressure of the solvent is lower in a solution than it is in a pure solvent. This leads to this expression right here, which is a little weird, but we're going to go through it. And what it says is you have a P0 on the right. P0, the zero symbol usually means pure in science. So that's saying that the vapor pressure of the pure solvent, that's what the little zero means right there. And if you take the vapor pressure of the pure solvent at that temperature and multiply it by the mole fraction, there's our chi we talked about earlier, the mole fraction of the solvent, that will give you the vapor pressure of the solvent in the solution, which is what we see on the left-hand side. So remember that mole fraction is a fraction. It can go as low as 0, it can go as high as 1, but it will never be more than 1. So what that says is whatever your vapor pressure of the pure solvent is, that's always going to be probably a bigger number, or at least the vapor pressure of the solution will be no bigger than it. So that means it's been lowered, all right? So they call this vapor pressure lowering, all right? The vapor pressure of the solvent in the solution will be less than the vapor pressure of the pure solvent. Those bouncer, those blocker solute molecules are preventing the liquid from going into the gas phase. So you have less gas over the liquid. That's where the vapor pressure lowering comes from. On the right-hand side in that picture right there, the big blue molecules, those are the solutes, the bouncers, the blockers, whatever. And they're blocking the water molecules from getting from the liquid to the gas phase. So on the left side, where there's no solute, lots of water molecules in the gas phase. But on the right side, when the solute's present, not as many liquid molecules in that gas phase. That means you're going to have a lower vapor pressure when the solution is present relative to the vapor pressure. The vapor pressure of the solvent over the solution is P solvent, the part on the left. And that equals the mole fraction of the solvent, not the mole fraction of the solute, mind you, but the mole fraction of the solvent, times the vapor pressure of the pure solvent. That P0 means pure vapor pressure. And in a nutshell, what that means, solution vapor pressure will be less than pure solvent vapor pressure. Raoult was the scientist that first figured this out. The vapor pressure is lower in the solution than it is in the pure solvent. And at first you might think, oh yeah, whatever. But actually there's some pretty cool kind of consequences from Raoult's law we'll talk about. And sometimes when people want species to evaporate, they will use Raoult's law to figure out the new value of how much vapor pressure is over the solution to make them evaporate easier. So there's a lot of uses for Raoult's law, as it turns out. So here's an example using Raoult's law. Let's use the same material from before. We had ethylene glycol, 62.1 grams. We placed it in 250 grams of water. We calculated that the mole fraction of the ethylene glycol was 0.0672. Anyway, let's figure out what the vapor pressure of water will be in the ethylene glycol solution at 30 degrees Celsius. All right. Now, why the 30 degrees Celsius value is important is you can look up the vapor pressure of water at almost any temperature. And at 30 degrees Celsius, if you look it up, the vapor pressure of pure water, 31.8 millimeters of mercury. So to figure this out, we need to figure out P solvent. That's going to be the vapor pressure of water in the solution. And that's going to equal mole fraction of solvent times vapor pressure of pure solvent. And 31.8 is P0 solvent. All right, that's the vapor pressure of the pure solvent. The answer we're going to calculate will probably be a number less than 31.8. So that's another kind of cool thing to keep in mind. Earlier, we calculated the mole fraction of the ethylene glycol, 0.0672, and we want the mole fraction of the water. Now, you could take moles of water and divide it by moles of ethylene glycol plus moles of water. However, if there's only two components, then mole fraction of ethylene glycol plus mole fraction of water will equal 1. So if you go 1 minus the mole fraction of the ethylene glycol, that gives you the mole fraction of the water, 1 minus 0.0672, mole fraction of water, 0.9328. So that's the chi solvent value that we need. And I want to point out once again, this is mole fraction of solvent, not mole fraction of solute. A lot of times when we deal with concentrations, we're more interested in solute, but in this case, focus on the solvent. 0.9328 mole fraction of solvent times the vapor pressure of the pure solvent, 31.8, that comes out to be 29.7 millimeters of mercury. So let's think about what these numbers mean for just a second. In pure water at this temperature, vapor pressure 31.8 millimeters of mercury. But in this solution here with ethylene glycol, where we have the bouncers, the blockers, the ethylene glycols, they're preventing some of the water in the liquid phase from getting to the gas phase. So the vapor pressure is lower. It's 29.7 when it was 31.8. This is the vapor pressure lowering phenomena. The vapor pressure of the solvent is lower in the solution than it is in the pure solvent. Okay, so here's a question. This has iodine, I2, in carbon tetrachloride, CCl4. And it says the vapor pressure of the pure carbon tetrachloride, 504 millimeters of mercury. What's the vapor pressure of the CCl4 over the solution? All right, so before we start this problem, let's just identify what's going on here. Carbon tetrachloride is the solvent. It has a vapor pressure, 504 millimeters of mercury at 65 degrees Celsius. And what we're doing here is we're putting a solute, iodine, in the carbon tetrachloride. So iodine is the solute, carbon tetrachloride is the solvent, and we have here an iodine in carbon tetrachloride solution, all right? So what we're looking here for the vapor pressure of the solvent, carbon tetrachloride, over the solution. So we'll use the vapor pressure in the solution equals the pure vapor pressure, which is this number right here, 504 millimeters of mercury, times the mole fraction of the solvent. So we have here 1.96 moles of carbon tetrachloride, and we have 0.0400 moles of iodine. So we're going to calculate mole fraction first. That'll be 1.96 moles of solvent divided by total moles, which is 1.96 plus 0.04, which happens to be 2. So it's like 1.96 divided by 2. That's going to be the mole fraction of the solvent. We'll then multiply that by the 504 millimeters of mercury value to give one of the answers listed down there. Now, before we start, though, the final vapor pressure of the solvent in the solution will be a number less than 504. So right away, you don't have to worry about A or B. A would be the vapor pressure of the pure solvent, but we have a solution. It's going to be lower. And 514 is a greater number than 504, and that doesn't happen by anything known to chemists. It's always going to be a value less than. Now, 10.1 and 1.96 seem pretty small to me, so my money here would be on 494 millimeters of mercury. Do the math to make sure. But if you do that, lo and behold, of course I knew what the answer was. I'm the instructor. But anyway, the answer, sure enough, C, 494 millimeters of mercury. So what I did here, this part right here, that's the mole fraction of the solvent. It's moles of solvent divided by total moles, moles of solvent plus moles of solute, and that comes out to be 0.980. And you multiply that by the vapor pressure of the pure solvent, 504. Sure enough, 494 millimeters of mercury. Good to go. Once in a while, you can have a volatile solute or volatile solutes. And if you have to figure out then what the total vapor pressure is, you can absolutely do it. It's just a little extension. So in Raoult's law, if you have not only a solute but a solvent, which is volatile, and remember, volatile just means you have a vapor pressure over the solution, then you just do mole fraction of the first one times the vapor pressure, pure vapor pressure of the first component, and you add it to the mole fraction of the second one times the vapor pressure, pure vapor pressure of the second one. And if you have a third one, you can do C, et cetera, et cetera, et cetera. So let's figure out here how this all works. In this problem, we have both heptane and octane, and both of these have a torr value. So those are vapor pressures. A torr and a millimeter of mercury are the same. So if they have a vapor pressure listed, that means that they're volatile. They're going to have a little bit of vapor pressure. And we want to do this so that we want to calculate the total vapor pressure of the system, but it also says that the mole fraction of the heptane is 0.15. So as we talked about earlier, with two component systems, mole fraction of the first plus mole fraction of the second equals 1. So we're going to first calculate then the mole fraction of the other component, which is the octane. So in this problem, if the heptane mole fraction is 0.15, the octane will be 1 minus that, or 0.85. And then what you want to do is just multiply the respective vapor pressures by their mole fractions. So if 31 torr is the heptane, we'll multiply that by 0.15, the mole fraction of the heptane. And then to that, we'll add the mole fraction of the octane times its vapor pressure, which is 11 torr in this problem. Multiply them together, add them up. 14.1 torr is the total vapor pressure in the mixture. So if you do have a volatile solute or something like that, you can absolutely calculate it. It's not too crazy. A little tedious perhaps, yes, but nothing you can't handle, and keep that in the back of your mind.